Okay, hello everyone. My name is Ahmed El-Banna. I am an assistant professor in the Civil Engineering Department. Welcome to the Nathan Newmark Distinguished Lecture for 2015-2016. This lecture series is intended to celebrate the memory of Professor Nathan Newmark, who was one of the old veterans of this university and the department head of the Civil Engineering Department for over 20 years. Nathan Newmark was a great educator, mentor, scientist, and professional engineer. He is one of the founding fathers of the modern earthquake engineering discipline. And he is also one of the great heroes for modern computation. He chaired the Department of Digital Computer Lab when it was starting here as well. Professor Newmark had several accomplishments in the professional practice, including a multitude of huge projects, such as the Latin American Tower that you see in the background here, that stood the 1957 and the 1985 destructive earthquakes. Other projects include the Bay Area Rapid Transition System, the Trans-Alaskan Pipeline System, and numerous or a large number of nuclear power plants. Academic-wise, Professor Newmark has made fundamental contributions to earthquake engineering, and up to this point, we still use, maybe a little bit modified, but his response spectrum. So Newmark response spectrum for earthquake design is still widely used. He also introduced to the computational community the celebrated Newmark beta integration method that's used frequently in dynamic finite element analysis. He has also made contribution to geotechnical engineering like slope stability analysis and Newmark charts for calculation of settlements under footing and distributed load at different depths. And this brings me to our speaker today, Professor Jim Rice from Harvard University. He would deliver the Newmark Distinguished Lecture. And when you have the responsibility of introducing somebody like Professor Rice, it's both a very easy and an extremely hard task, because I could just say, welcome, Jim, and that would be sufficient. Or I could spend maybe most of the lecture just going through some of his accomplishments. And so I put down some of the slides here that hopefully would help commemorate the point. And this is a very humble, and you see I had a hard time just filling the slides in the beginning. So this is how it started with me. And then I chose to just show you some of the longitudinal section on some of the great accomplishments that Jim has made to mechanics, computation, geophysics, and fracture mechanics. So it all started here. This is just a schematic, not to scale, for Jim, to prove that he was a normal human being when he started. And then he went on to join Lehigh University, which is the same university that Professor Fahrenstock has graduated from. And amazingly, he finished all his degrees in 6 years. So he joined as an undergraduate, and after 6 years, he graduated with a PhD. Again, this is a sketch. I'm not sure that Jim looked like this. And then amazing things happen afterwards. So shortly, maybe a few years after his graduation, he introduced the J integral, which initiated the field of nonlinear fracture mechanics. I was surprised to find that in the same year, he has the RR model, which for the stress fields around a crack that propagates in a plastic material with a power law hardening rule. And then this came to be known in the literature as the HRR model because of also the contribution of Professor Hutchinson. In 1971, Jim has another foundational paper that introduced the plasticity theory with internal state variables in a thermodynamically consistent way. And then he has the ductile to brittle transition, or brittle to ductile transition model in crystals with Thompson in 1974. Another foundational paper with Rudnicki that introduced the concept of strain localization and conditions for loss of instability in plastic material with pressure sensitivity. And during that time, also in several papers with Bob McMeeking and others in the 70s, he introduced a computational algorithm for elastoplastic finite element with finite strains, large formation. And so at this point, I think the community realized that regardless of how young Jim is, we must do something to him. So in 1980, he joined the AAAS, which is the Advancement or American, I forget, but it's an American Advancement of Art and Sciences. I got it right, okay? Academy, which publishes the Journal of Science, okay? And then he also joined both national, like he was elected to both of the National Academy of Engineering and National Academy of Sciences, and both are when he was still maybe 40 years old. So this is a unique thing. And then the great things continue to happen. In the 80s, maybe lucky for us who are interested in earthquake mechanics, Jim got more interested into the physics of earthquakes. So in 1983, he has a paper that pinpoints the main ingredients for a well-posed friction formulation that to be used in fault mechanics. And I will make a little jump. This is to 1993, and this is not because Jim didn't do anything in these 10 years, but just tomorrow there's another lecture, and they have to find something to talk about, and there's a lot, so it's, I don't want to repeat myself. So in 1993, there was a very big issue taking both the mechanics and physics community about why earthquakes happen with apparently a large distribution of sizes. What makes an earthquake stop? What makes an earthquake nucleate? And how this complexity can be sustained. So Jim had some beautiful papers in this period related to this topic of spatiotemporal complexity of fault slip. And then in 1995, there's a new mode of rupture that was discovered, particularly for earthquakes, in which a mode 2 crack would propagate and lock behind it to form a localized pulse instead of a crack. So Jim was among the pioneers who provided a rigorous framework for when this type of rupture could happen on a frictional interface. So the first paper, I think this was Byrne in 1995. It pinpointed some aspects of complementary to the friction that makes the fault lock after it ruptured. During that time, there was another fundamental paper by Gubel and Rice, which introduced a spectral formulation in 3D elastodynamic fractures. And then in 1998, there's a fascinating phenomenon that Jim and Maurici discovered about crack front waves. These are persistent perturbations that propagate along the crack front as it propagates forward. And they analyzed conditions under which this perturbation persists and the implications for that. In 1998, and this is personally not one of my favorites, because many of Jim's papers are favorite for me, but this one directly affected my thesis. So the slip pulses or cracks, under what conditions a friction low operating on an interface could allow for the self-healing pulse versus the ordinary crack propagation mode. And another very fundamental paper for me is with Lapusta. And in this paper, they introduced maybe the only model until now that can consistently simulate cycles of earthquake, taking into consideration both quick or fast dynamic ruptures and slow interseismic loading. So that was an amazing accomplishment, which will have in the following years tremendous applications for hazard and understanding of earthquake physics. And luckily for me, Lapusta joined Caltech a few years after graduation, and I enjoyed being a partly her student. So she co-advised my thesis at Caltech. In 2001, Jim and Needleman and Michael Falk presented a paper in which they pointed to a very long-standing problem in cohesive fracture, and that's when people use either intrinsic or extrinsic cohesive loads to simulate fragmentation. If they do this naively by putting the cohesive load everywhere in their finite element mesh, they will not get a convergent solution. So the solution will be ill-posed in the numerical sense. So Jim pointed out to this important aspect. And then, although Jim doesn't do experiments per se, but in 2005, there was a new experiment at Caltech from Aris Rozakis' group that introduced or developed a framework for simulating ruptures that mimic earthquake. This came to be known afterwards as earthquake laboratory experiments, or laboratory earthquake experiments, and Jim was involved in the birth of this very exciting experimental technique. In 2006, another foundational paper for Jim that laid down the framework for the multiphysics problem of earthquake rupture, including thermal and pore fluid processes, and that was very important. And then something important happened here, I will tell you later. And then more recently, with Hiroyuki Noda and Eric Dunham at Stanford now, they developed or they presented maybe the only model existing up to this point that implements laboratory-based friction parameters in a realistic elastodynamic simulation. And although the the fault they represented is very short because the mesh size was extremely fine, but that was required like supercomputing capabilities and still standing as the only model that has been presented now. And in this 2009 paper, they also solved not only the frictional problem, but with pore fluid diffusion and thermal heating. And this is what happened in between. So, of course, this is not on the timeline of Jim. This is on the timeline of myself, because this is my first picture with Jim. So Jim came in 2006 and gave a lecture at Caltech, which was about his 2006 paper, and that affected me personally a lot because it says, well, there's a future in this kind of problems, and it's a very exciting one. This picture was in my first SCIC meeting, and those who know me know that I smile a lot, but you can see here that it's extremely exaggerated because this is when Jim is kind and supportive, that's the feeling that you get. So indeed, Jim is a very unique mechanician, and we are very fortunate to live in the time where Jim is here to enlighten us with a lot of insights into extremely interesting problems in different areas in mechanics. Tomorrow I will show some other stuff that I haven't shown today, but for the sake of time and to let you enjoy Jim's presentation, I would like him to come over to the stage and enlighten us with his recent work on fault mechanics. So please join me in welcoming Jim Rice.
Thank you, Ahmed. I wasn't sure who you were describing there in much of that. Ahmed mentioned a 2006 paper I wrote, and that's also the title of this lecture, but I'm going to tell you at least a few things discovered since 2006. So this is work with a lot of colleagues, not all of them, not all of the collaborations resulting in joint papers, but nevertheless, it's the group with whom I've been doing a lot of work on this theme. Nicholas Brontu was a postdoc. Eric Dunham was also a postdoc now at Stanford. Nadia Lapusta, Ahmed mentioned at Caltech. John Platt at Carnegie Institute was a graduate student. John Rudnicki was also a graduate student, but many, many years earlier, and we have been collaborating again lately. Terry Tullis was an old friend from Brown. Massimo Coco in Rome. David Goldsby was at Brown, just moved to University of Pennsylvania. Hiro Noda came to Harvard to get, quote, theoretical training, in the words of his advisor who sent him there, and did marvelous work on rupture dynamics, which you'll hear a little about, and is now at the Japanese group for ocean and meteorological studies. Alan Rempel worked on some of these heating and weakening topics and is at University of Oregon. And Victor Tsai worked briefly on this, but much more with me on something I'll talk about tomorrow on glaciers. So here's a long-standing quandary we have in seismology. Lab measurements that were thoroughly summarized in a famous 1978 paper by Jim Byerly show very clearly that everything you could think of as a candidate rock for a fault zone has a quite high friction coefficient of the order of 0.6 to 0.8. Furthermore, Mark Zobak, sometimes with Mary Lou Zobak, sometimes with others, did a large amount of borehole study of fault zones to try to get in situ stresses. And he did confirm that in many cases in the field, ratios of shear stress to normal stress on faults do fall into this range anticipated from Byerly's lab studies. And here we think of the shear stress as friction coefficient times normal stress minus pore pressure, and we always want to be thinking of pore pressure in thinking about faults. Now, we've also learned in much more recent years, and I'll shortly show you some of the evidence, fault slip zones are incredibly thin. We've been fooled for many years by the fact that there are broad damage zones about faults, which may run anywhere from a meter to a kilometer. But in fact, the actual part that seems to support large slip seems, at least in many cases investigated, to be extremely thin on the few millimeters scale. And so again, I'll show you that evidence later, but you can see the problem. If you're dissipating all of the energy, and these friction coefficients imply particular large shear stresses. If you're dissipating all of that energy over such a thin zone, and if the fluid pressure is somewhere near hydrostatic, then you ought to generate a lot of heating. You ought to be able to go anywhere along the San Andreas Fault and measure substantial heat outflow. And you also ought to find extensive signatures of previously melted faults in the form of what's called pseudotachyllite. And the point is, neither is found. For years and years, people have been looking along the San Andreas system and other systems for examples of this, and you don't find it. Now, it doesn't say that, let's say, at much greater depth, that some of these things would not be abundant, and indeed, most evidence for melt or pseudotachylites does seem to come from regions deeper than, say, 15 kilometers in the Earth. Now, a major change in the way we thought about faulting came about in the early 2000s, and in particular, 2003 seemed to be a banner year for this. Here we're looking at a section. You can barely see, I'm sure, but there's a black arrow here and another black arrow there, and that marks an extremely thin zone. We're looking at an exposed part of the of a fault here called the Punchbowl Fault. The Punchbowl formerly played the role of the San Andreas Fault. In its lifetime, it accumulated something like 35 kilometers of slip, presumably in earthquakes, and ultimately got taken over by the San Andreas Fault. So the plate motion that is now being accommodated on the San Andreas for a long, long period was being accommodated on this Punchbowl Fault. And the point that Judy and Fred Chester made is that, in fact, this slip seems to have been accommodated on an incredibly thin zone marked by those black arrows. And then with David Goldsby, they made thin sections here. So here's a blown up scale. That black line is 5 millimeters. So this light area, which contains the slip zone, is about 1 millimeter wide, and the actual localization within it is sub-millimeter. So you have this remarkable feature that all of this tectonic slip accumulated over millions of years, or at least hundreds of thousands of years, happened apparently on a very thin fault surface. So that it was an amazing surprise, because for several years the community had understood when you look at a fault, you see a broad damage zone about the fault. But it doesn't seem that that broad damage zone accumulates much of the slip. That seems to be highly localized. So that has been long a puzzle to study. Now, in that same year, there was additional evidence that came in 2003. Borehole studies completed in '99 through the fault that ruptured in a big earthquake in Taiwan called the Chi-Chi earthquake of 1999. That too discovered that the borehole or the core was penetrated by the fault rupture, but with the fault rupture being extremely thin in the same range as for the Punchbowl Fault of 50 to 300 microns. So that was same year, and indeed these investigators surprised one another with their results, these and the Chester and Chester that I just showed you. Now, we don't always get such extremely thin zones, but we get pretty thin zones. These are two other penetrations at different depths of that same fault that ruptured in the Taiwan earthquake of 1999. Here for one hole punctured at, at the depth that you see marked here, 11-10 meters or so. The shear seems to be confined to a zone 2 centimeters broad, and for another case, the zone is about 3 millimeters broad. So it's not everything in the sub-millimeter range, but some is, and everything is narrow. Now, why were we surprised about this for so long? And part of the reason is shown here. So this is a messy picture, but we're looking at features exposed in a trench. That trench was made across the fault, the Johnson Valley Fault, the first fault of a complex of fault segments that ruptured in the 1992 earthquake in the Mojave Desert area. And the thing you see is that, yes, at the surface things are a mess. There's a broad damage zone, lots of ruptures reaching the surface, but as you go down in depth, things simplify considerably. And ultimately, a few meters deep, you reach a point where it looks like all of the action is happening on a single surface. And in this and other cases studied by Benzine and Rockwell, they found thicknesses of the shear zone on the order of 1 to 2 millimeters. So all of this has, as I said, been quite a surprise. I myself had to throw away work I had been working on for some years that kind of assumed that an earthquake rupture on a major fault involved significant shear over at least a meter thick shear zone. And now we realize that guess was off by about a factor of 1,000 or so, at least in some cases. This is another picture. It's just a hand-drawn schematic of structures near the median tectonic line fault. And it's a funny logarithmic scale, so you can't get much quantitative from this. But the people who did it, Wibberley and Shimamoto, did measure the thickness of their fault zone, again, very thin. But that's not why I put this picture up here. I put it up because what these folks also did, in a tremendous service for this area, is take multiple samples, boring out cylindrical samples, taking them into the lab and studying them in triaxial apparatus. And in that way, they were able to determine features like the drained and undrained compressibility of the material. Undrained means you just let the fluid flow in or out as it wants to keep the fluid pore pressure constant. Drained, of course, means you don't allow flow. They also measured permeability, and they did it with several levels of confining pressure on their cylindrical samples, running from 50 to 200 MPa, and then also studied the effect of path. If, for example, you first compress up to 200 MPa and then decrease to 50, that's quite different from cranking up to 50 directly. So there are plastic or irreversible effects. But it is the source of most of the data we could put into our models, the studies of this fault zone. Now, the fault gouge itself is very interesting, I think. And this study by Chester et al., published in Nature in 2005, showed a remarkable fractal distribution, a pure parallel distribution. It's a distribution which has the properties that it would actually overfill space at the small size unless the distribution was cut off at small sizes, and that cutoff seems to take place in the neighborhood of order 10 nanometers. So when we think about localization in granular materials, there's a great literature, I think, as most of you will know, on granular materials. And a lot of the attention has gone to, well, how thick are localizations in granular materials? And typically, one sees estimates on the order of 5 to 10 times the mean particle size. If we use the particle size here, for which 50% by mass of the aggregate is heavier and 50% smaller, that would be about 1 micron. So that would suggest 5 to 10 microns if we use that standard granular materials guideline. But there are two things to be cautious about in adopting that. First, almost all of the granular materials studies which have looked at localizations and tried to characterize them have been done for very narrow ranges of particle sizes, nominally identical particles or slight variations. This is just a gigantic variation in range in this fault, so we're not sure how adequate those classical results from the granular materials literature are on telling this thickness. Okay, so this is the program then. We know that faults are frictionally strong, or fault materials are frictionally strong when studied in the lab, but somehow they must become dynamically weak. And there are a couple of processes that are important from the start of seismic slip. One that I'll get to later, I'm not sure why I put it in that order here, but is flash heating. It's a process that had been known in the classical friction literature, descended from the studies of Bowden and Tabor in Cambridge, UK in the last century. But another is thermal pressurization of pore fluid. So what am I talking about here? Well, any fault in the Earth's crust, you should make the default assumption that it's water saturated, at least where you're above the local water table. Excuse me. Now, if you start to shear this material, it's going to get warm. The thermal expansion coefficient of water is about 50 times bigger than that of the surrounding rock. So the water has a problem. It can't fit anymore in the space assigned to it. And of course, what that means is it induces a monster stress on itself. The friction, or monster pressure, the friction strength is proportional to total normal stress minus pore pressure. So raising the pore pressure greatly reduces the frictional strength, and that is thermal pressurization. Later we'll get to other processes on this slide, but I wanted to say a little bit more about thermal pressurization. Well, it's highlighted in red there. That's saying something more about it. But really what I wanted to say is here. It's a very interesting history, and I put this up partly because, as Ahmed mentioned, Nate Newmark was also interested in nucleating landslides, and his work in that area continues to be very influential. But this is a tale of two literatures, the people studying landslides and the people studying earthquakes, who took a long time to find out that one another exist. So first, Frenchman Habib, I believe working at École Polytechnique in Paris in '67, wrote a paper suggesting that pressure generation in rapidly sheared, saturated materials would be important to making landslides happen easier. Then a few years later, Rick Simpson wrote a paper. Rick is a geologist working on faults, suggesting similar things, but apparently unaware of that previous work. And then Habib wrote, again, a more detailed paper on this process, not mentioning Simpson. Of course, at that point, he might have been annoyed that Simpson didn't mention him, but I think that simply people weren't aware of one another. Later, a man named Anderson wrote a very complete paper on this thermal weakening mechanism, but again, not being aware of the earthquake literature. Then Lockenbrook, in the earthquake literature, wrote a paper on frictional heating, not being aware of any of the landslide literature. And so on it goes until the early 2000s, when these two streams of the literature actually discovered that one another exist. So now we have a happy community of folks in that broad area. Or these are more examples of that oscillation back and forth between those literatures. Okay, so here's a very simple model for thermal pressurization weakening. We've got a ground-up fault gouge here, and we're sliding one side of the fault relative to another in a typical earthquake. We do very simple calculations when we can get away with it. We are sliding at a constant velocity, which we take as about a meter a second. Now, why a meter a second? You could look at slip inversions like those that, for example, Tom Heaton, Ahmed's advisor, have done for earthquakes. These inversions attempt to say how much slip occurred at a different place and how long did it take to have that slip. If you take the ratio of those numbers for various earthquakes that have been studied, the ratio of amount of slip to duration clusters around a meter a second, give or take about 30 or 40%. So this is probably a reasonable 1 meter a second, a reasonable number to take. And we're assuming that all of the inelastic deformation is confined to that gouge layer. So here's a mathematical description. It's the same one would use whether you're talking about a fault zone or a landslide zone. But mechanical equilibrium, because we're dealing with zones which in the end will turn out to be very thin, it's no need to include mass times acceleration terms here. Basically, the shear and normal stress are uniform across the shearing zone. The frictional working, stress times strain rate, raises temperature. And of course, non-uniformities in temperature cause heat conduction, so there's a divergence of heat flux that multiplies that. So that's a classical energy equation that I'm sure most of you have seen before. And then in a related way, conservation of fluid mass has to be invoked. As you raise the temperature, the pore pressure raises just because the fluid wants to expand more than the host rock and it doesn't fit anymore. But as you create non-uniformities in pore pressure, that drives Darcy-like fluxes, and the divergence of that fluid flux balances out the conservation of fluid mass. Now, you could have long discussions, and Ahmed and I do this frequently, about how to represent frictional sliding. In this work, we've tended to assume that the friction is rate strengthening for one reason, that often is the observed situation at high temperature. That is to say, the friction coefficient goes up weakly with strain rate. And by the way, if we did not assume rate weakening, actually the game would be over. There would be no need to discuss localization anymore, because the math says if you had a friction coefficient that was constant, these equations only have solutions where all the action happens on a mathematical plane. So that's severe localization. Well, that set of equations was first formulated and solved by Art Lockenbrook, and he found this simple, and he envisioned shearing the two sides at constant relative velocity v, and he found a simple exponential decay of stress with slip, and that's where things stood for a number of years since the time of his paper, which was 1980. But then John Rudnicki and I, we actually started this some time ago, and because we're both old and tenured, we're not in a hurry to publish, so there was a bit of a delay getting this out. But what we found is that the Lockenbrook solution is actually, in general, unstable. And it's unstable in a way which allows localization. So for example, you can ask, if you perturb this solution, so imagine you have steady shear flow, but you perturb the solution with an e to the I k y kind of spatial perturbation, you can figure out the, sorry, got out of hand there. You can figure out the longest wavelength for stable linearized response. And there is a finite longest wavelength, and any perturbation longer than that would give you a growth of the perturbation with time. So that wavelength or half wavelength is a good candidate for the estimate of the thickness of the shearing zone. And we can put in a few values based on direct laboratory measurements of properties, which put that down in the few microns range, different numbers for different depths. 7 kilometers you might think of as a representative centroidal depth of the region that ruptures in a crustal earthquake. But if you're working in the lab or boring down to a kilometer depth only on a fault, you would get bigger numbers. But a few microns to a few tens of microns. Now, one of the big problems we have in saying, how do we think about this in a real earthquake, is that the earthquake rupture it's basically a mode 2 crack propagation. As the rupture comes along and approaches a given point on the fault, you have massive stress changes associated with the rupture tip. That certainly has to deform and crack up or otherwise damage material. And we don't have very stringent guidelines for guessing how much that alters permeability and compressibility, the two things that would be most susceptible in this scenario to damage. But what the red represents are wild guesses, and I can't say much more about them, as to what might actually be correct in the field situation. So about an order of magnitude bigger than those based directly on the lab. Okay, now John Platt in his PhD thesis did this paper on full numerical simulations of the system of equations I showed you. And here's a typical simulation. I should also point out the Lockenbrook solution, the one I just showed you, assumed that these were just blocks that would not conduct heat or fluid. John Platt treats them as poroelastic half spaces, so fluid can permeate into them, and they are not rigid. They can deform elastically. And he has slid this at 1 meter a second. I explained why that's a sensible number earlier. And calculates what is the distribution of shearing through this gouge layer and what is the stress involved. And the kind of thing that results is like this. So here's an example. H here, the thickness of this layer, was taken as 1 millimeter. I think the pointer is giving out on us a bit, but let's see. Do you have another? Okay, well, while we're getting the pointer, I'll point the old-fashioned way here. And so this layer in the simulation you're seeing is 1 millimeter thick. But what we find is that the shear localizes, oh, thanks very much. The shear localizes down to a tiny fraction of that. So here, as it says, the deformation is localized to a zone 43 microns wide. A millimeter is 1,000 microns. So that shows you the extreme localization that these equations predict. And it's not, we think, completely unlike what we see in nature. So basically, we started deforming this whole region, but ultimately all the deformations localized into a tiny fraction of that region. Here's what happens to stress. Of course, the shear stress, which scales with the difference between normal stress and pore pressure. As you heat up that water and as things localize, so you're heating much more intensely, the strength goes down, so you have an initial result which follows the Lockenbrook analysis, which assumes no transport of heat or fluid mass out. Ultimately, we diverge because our calculations include heat and transfer to the outside. And then at large enough slip, you start to become asymptotic to another classical solution, which is the solution for slip on a mathematical plane. That was first done by Mace and Smith. They had actually done it for fluid diffusion only, not looking at thermal diffusion, and a small change, which I found makes their solution valid for thermal diffusion. So you go from uniform slip through the whole layer, which quickly destabilizes and ends up with a slip so localized that you cannot distinguish it from sliding on a mathematical plane of zero thickness. Thanks. Okay, so we're getting recharged now. Now, does this analysis have anything to do with reality? Well, some seismologists are deeply suspicious of things you learn in the lab as supplying a vision of reality, but I'm not among them. And this is a collaboration of Platt with Tullis and Goldsby to check these predictions. So what they did was take a rotary shear apparatus, steel apparatus, put a layer of the sedimentary material in it, fluid saturated, and sheared fast, and up to the first 10 seconds or so of the experiment at various shear rates, they got pretty good agreement with the theory, but then things started to diverge, and they have attributed that divergence. They might just be being too kind to the theorists, but they have attributed it to the effects of having highly conductive material, steel, a small distance away from the shearing zone, which ends up messing up the heat transfer analysis that's done as part of the prediction there. Now, that solution for slip on a plane was used by me as part of a 2006 paper to go another step and ask, what is the fracture energy of earthquakes? G is a very common symbol for that, a shear fracture energy. And there's something that you could actually estimate from seismology, which you could argue ought to always be comparable to G, but not quite identical, called G prime. So from purely seismic estimates, you need things like the estimated stress drop in the earthquake, the estimated amount of slip, and the depth of slip. You could figure out this, but that's the data set, and this black and red lines are attempts to fit it with this simple model. Well, the data has monstrous amounts of scatter, but nevertheless, there's a rough trend there that up to sometime I think I went this, up to sometime in mid-September I was quite happy with. Then it turned out a former student of mine, Rob Vieska, and a former sabbatical visitor, Dimitri Garagash, published this paper in Nature Geoscience. So they had looked at this whole thing again. They had improved calculations that I did. I'll show you a little bit of what they did different. But they had also found in the literature that the authors of papers giving some of the fracture energy values that I had used discovered that they had made a mistake in what they reported, and all of those values had to be increased. And in any event, this is their theoretical plot. So that's not bad. And the way the ingredient they use to convert amount of slip inferred indirectly from seismology into work done on weakening the fault, and hence what is called fracture energy here, is to use a solution that Garagash had published in 2011, which I think certainly improves on my procedures, but it does give a pretty impressive result in the end. Okay. So much for thermal pressurization. That was thermal pressurization of native pore fluids that we assumed were already in there, as you would expect to be in any porous region in the Earth. But the next process I want to describe is a kind of fluid pressurization, but it's different in the sense that it relies on chemical reactions, thermal decompositions. When you rapidly shear certain minerals, you can produce a product phase that includes volatiles or vapor at very high pressure. For example, carbon dioxide from carbonates, water from clays or serpentine. And this is a little schematic of that. So some of the field evidences were, for example, after that 1999 Taiwan earthquake that I've mentioned, Hirono et al. Reported changes in clay minerals along the fault, suggesting that they had taken part in some kind of a reaction. And then also in high-velocity friction test in a rotary apparatus that I don't have time to tell you much about, Han et al. Found that they could detect through a meter in their lab the increase in CO2 in the lab air. So evidently, decompositions were actually happening, quite relevant to earthquakes, but also going back to Nate Newmark's interest in landslides, also relevant for landslides. And in particular, a couple of groups now in the last year or two have proposed that the massive displacement of the Hart Mountain complex in the western U.S., I think a slide of order at least 15 kilometers displacement, was in fact due to thermal decomposition along the surface. So there's some suggestion, and perhaps one could even say evidence, that this is a process that can take place in large landslides. Okay, I'm very poor at chemistry. It was my worst subject ever, but fortunately we worked with Nicholas Bruntu, who was much better than this. But these are examples of thermal decompositions in carbonate rocks. I won't go through the sequence of reactions. In clays. And a very good lab material to use is gypsum, because while you wouldn't want to be too close to an experiment that was running at 500 or 700 to 900 Celsius, you might not be too uncomfortable with running next to something at 100 degrees Celsius. When you boil your water for tea or coffee in the morning, that's what you have. And gypsum is a good material for that, and it was used in Bruntu's PhD thesis at École Normale Supérieure. So now I'm going to show you some experiments which we think were dominated by exactly that kind of decomposition in a carbonate rock. And they involve this rotary shear apparatus of Shimamoto that I have briefly alluded to. Shimamoto is too old to continue to work in Japan. They forced retirement at a very young age, so he's been going around the world installing these delightful test machines at different universities. So I don't know if anyone here at UIUC needs such a machine, but I can give you Toshi's address if so. So here's an example of a suite of experiments. This is friction coefficient versus amount of slip on the fault, or fault displacement in meters here. And it's a jumbled mess, but basically as you come down here, you're going from very slow slips, 0.08 meter a second, down to 1.18 meter a second. And these faster slips are in the range of what we think to be representative seismic slips. So because that's so cluttered, I'd like you to focus, please, on these two diagrams at the bottom, which are at a given normal stress. So this shows you the friction coefficient that you get ultimately if you sustain the slip for a fair amount of slip, several meters. Then ultimately you end up with the friction coefficient, which becomes less and less the faster that slip rate is. So that is thermal weakening. And here's another way of looking at the results again. Here's the shear stress supported as a function of normal stress in slips at rates which correspond to average earthquake slip rates. And you can see that if you look at the stress at the beginning of slip, it is typical frictional results with a friction coefficient of order 0.6. But if you look at the results after sustained slip of a few meters, the friction coefficient is reduced by an order of magnitude from 0.6 to 0.06. So these are really pronounced weakening results, and I think the community is still in the midst of trying to fully understand these. At least my own group is quite in the midst. So what changes in the description I gave you for thermal pressurization? Well, not much. You've got a lot of thermochemistry to deal with here, but in the end, it can all be summarized this way. Suppose C is the extent of reaction, and for simplicity, assume the reaction has Arrhenius temperature dependence, and we allow the possibility that you could completely deplete the reactants. That's this 1 minus C term here. The C is the extent of reaction. And basically, having the chemical reaction go on can all be described by a factor E, which describes how much a unit of the reaction has buffered what otherwise would have been a temperature rise from the stress working that's being done. And coming down here to fluid mass conservation, you can say this coefficient P tells you how much the pore pressure increase is different from what you would have had if you did not have the reaction. You are creating this fluid phase, of course, which wants to occupy a much bigger space, so P is a large number and an appropriate metric. And just to prove that there are numbers that can be put down for all of the parameters involved, here's a case for CO2 release and 3 cases for H2O release. And those important parameters, E and P, are over here on this axis. And from them, we can estimate shear zone thicknesses. Unfortunately, with thermal pressurization, there's no really believable linearization you can do. It's because of the very strong variation of the Arrhenius term with its parameter. So we can make crude linear perturbation estimates. They are, as it turns out, in the ballpark of more detailed numerical studies, but they really can't be trusted very much. So here's an example of what happens if you begin with a granular lithology that is wet and hence subject to standard thermal pressurization, but then as it gets hot, you can start to force it to undergo decomposition reactions. So you get a multi-stage weakening, at least that's what's predicted by the concepts that I've outlined. Now, this thickness, why did I do that? Yes, the thickness of what's being studied here is 1 millimeter. So again, we're looking at severe localization. And here is a picture of what we get for strain rates on a color scale and reaction rate over here on a color scale versus distance, but the distance goes from -0.5 millimeter to +0.5 millimeter. And you can see just the hyperlocalization of shear that results. You can also see what happens as reactants gradually deplete. And this zone, you can see here a slight broadening of the localized zone, and that's associated with depletion of the reactants. Another case where we ask, what happens, there was a coefficient of A in front of the Arrhenius term. If you increase it by 1,000, does that make much difference to the thickness of the localized zone? And the answer is not much. You do tend, in this case, to start to see early depletion of the reaction, but the thickness of the localized zone is not significantly different. Now, here's an interesting phenomena that can happen. As you start to deplete the reactant, you can no longer continue to shear where you started. And as this coloring goes down, the strain rate is diminishing, but also if you look over here, the reaction rate is cutting down simply because the system is running out of reactant. And it has to renucleate if it's going to keep deforming on one side or another. And it's a matter of round-off error in the computer program that chooses one side versus the other. But the idea is this system reactivates elsewhere, and it may die there or it may continue vigorously. But in any event, if you think, well, what happens if this process happened and you're a geologist who comes back 1,000 years later or whenever, and you look at the fault? Well, what you would tend to see from that is a laminated structure, because once the locus of the reaction shifted, you would see all the activity seem to be going over in a lamination or a zone different from the other. And Tom Mitchell sent us this picture. He's at University College London, of a specimen which was undergoing a carbonate decomposition. Unfortunately, it cracked here. Tom swears that that happened after the thing was taken out of the ground, but you can see what looks to be like evidence from this white stuff in here of a laminated shear zone. Okay, I think that's almost it. I would like to say a few words about this final thermal weakening process, flash heating. And this got its start around the turn of the century. It builds on old ideas in the metals physics literature on friction from that group, Bowden and Tabor, and others at Cambridge. But the idea is simple. When you put two solids together, they contact at asperities. Those asperities operate at what seems to be pretty much the theoretical indentation strength of the material. So the normal stresses are absolutely massive. The shear stresses have to be whatever you would measure as a macroscopic friction coefficient times the normal stress, if the macroscopic shear tau is going to be proportional to the macroscopic normal stress. And that forces us to say that rocks and many ceramics operate with frictional shear stresses of the order of 1/10 of the elastic shear modulus. So that is a very big number. And what does that mean? Well, if you start to slide the top here relative to the bottom, you're going to be heating at that shear stress times the sliding rate V, and you're going to heat until you've slid the contact out of existence, and then it's going to quench rapidly when it's not touching directly other hot material. So if you think of how to think about the contact shear stress, you could think of it as being whatever it was at initial temperature, but then as things get almost hot enough to melt, you should have a fall in shear stress at a certain temperature, which is simply called the weakening temperature, T sub W, in this analysis. And you can make, if you can guess the weakening temperature, which typically we associate with the melting temperature, but if you can guess that, then you can figure out a weakening velocity. And the idea is when the actual sliding velocity is greater than this number, which depends on thermal diffusivity and diameter of the contact region and other things, then the asperity is weak for some part of its life. So that suggests a friction coefficient that would be written as a function of velocity, which has normal friction for the fraction of its life before the contact has gotten hot, and a weakened value of friction times the fraction of its life for which it's been severely weakened. And that finally can be rearranged to a constant term plus another term that goes as 1 over velocity. And that has some power in fitting data. The first data that came out was very, very noisy, done by Tullis and Goldsby, but as I'll show you, they've since cleaned up their act. But one of the nicer bits of early data was done on what's called a Kolsky bar, a bar that is clamped here. The bar has been pressing a rock annulus into a rock background, a particular quartzite in this case. And a clamp has been put in. This part of the bar has been twisted, and then the clamp released, so an unloading wave propagates in, rotating the apparatus, rotating the tribopair, or one side relative to another. And by the way, this quartzite has a friction coefficient of about 0.7. But what you find is that the actual coefficient of friction falls down to around 0.02. So a massive drop from normal friction due to the fact that there's high sliding velocity. And how high is the velocity where you read this on the right scale? So it's of the order of a few meters a second. Now, experiments have their problem. That's why I'm a theorist. This dashed line is put here because that's really the last of the points that we can believe, because the wall of the apparatus broke. Terrible things like that happen. So, but in any event, over the good part of the experiment, you see there really was a very low friction. Now, going back to work of the Brown group, they have a marvelous paper that came out in Science in 2011. They had cleaned up some of the oscillations in their experiments, but they find fairly good agreement with this kind of description with a lot of scatter, but you can see a normal static friction of coefficient, and then above a critical velocity, which tends to be in the range of 0.1 to 0.2 meters a second for these rocks studied, you have this fall off, which is crudely fit by a 1/velocity law. I'm not sure anyone knows the explanation of all of this ringing, and also what I don't understand is why this feature at the end, the way the experiment is done, it was an increase in velocity from the velocity at this point out to here, and then a decrease in velocity, and presumably the apparatus was maybe subjected to some kind of perturbation when that change was put on. But in any event, that's what we have. So it seems to resemble in some ways what we would expect for flash weakening. Now here's a more recent experiment done by a group which my student John Platt joined in trying to help them make quantitative sense out of things. So here's what the flash heating model would predict. And then John had the brilliant insight that during this part of the sliding, even though the flash heating process was going on, the aggregate of that process over all asperities was heating the sidewalls. So then when he tried to look at what happens for the deceleration phase, he corrected the theoretical formulas for the temperature rise that occurred in the sidewalls during the acceleration phase, and that gave a pretty good fit. It looks like it only fits over a little distance on this graph, but that's a log scale, and it actually fits over about an order of magnitude change in strain rate. So that's pretty good, and it convinces us that this is probably a real process. Now, it probably is not an important process, the same investigators have concluded, for gouge, in the sense that if deformation is really distributed through gouge, you have hordes of contacts, and let's see if I have a punchline I can read you on this. Yes, the total slip in a simple model is assumed to be shared between all of the contacts, but you do get a prediction of flash heating, but the rate to achieve it is rather high, of the order of 4 meters a second versus 0.1 meter a second for bare surfaces. And it's simply a much less efficient process in gouge. So for flash heating to be important, we probably do need something pretty close to bare rock, touching bare rock. Okay, so I've run terribly over time, so I'll try to quickly summarize here. I'm going to just jump totally through one section of this, and which tries to use some of these dynamic weakening laws in modeling earthquakes, and go on to this, which I propose we might think of as the future of rupture dynamics, or at least of this kind of study. We really would like to have numerical procedures, and I don't know how to create them, but numerical procedures that are versatile enough that when we think of what we normally treat as sliding on a mathematical plane to represent an earthquake rupture, we want to think of a thin zone which has sustained or will naturally sustain localization. And we want to think of these, if we have chemical reaction or chemical decompositions going on, we want to think of these equations, or if no reaction, then the versions without the extra terms, as going on on that thin zone. And this then is a prescription for relating history of strain rate and stress to the pressure and temperature, which in turn tells you what the stress actually is. And this is the kind of model for the future, if we can get there, that would be good to have. I felt particularly happy about including slides in this building of the National Center for Supercomputer Applications, because it's the kind of thing which might be a very good target for such studies in the future. Okay, let us. Yeah, I think I jumped a few things here. Well, I think I seem to have things out of order a bit, but let's. Yeah, I'll mention one study which I think is an interesting one. Hiru Noda and Nadia Lapusta at Caltech re-examined that 1999 Chi-Chi earthquake, and they used results that they could determine that in the north, the friction was velocity strengthening and slow slip. That means it's the kind of friction where you can't easily nucleate an earthquake. However, it was less permeable than the material in the south where the Chi-Chi rupture started, and hence would be susceptible to co-seismic thermal pressurization if you could just get slip started there. And in the south, the friction was unstable, what in rate and state friction we call velocity weakening friction, so a great place to nucleate an earthquake, but the region was more permeable, so thermal pressurization weakening would not be as strong. So that is, in any event, their explanation of what seems to be a good way of thinking historically about earthquakes in this region. This is distance along the rupture zone. And the idea is that you have frequent earthquakes in the south. You're seeing slip versus distance here. So these little bulges are the slips in individual earthquakes that get nucleated. And most of these earthquakes start and stop in the south, but occasionally there's enough stress to activate the northern part, and the northern part is much more susceptible to extreme dynamic weakening and creates big events like the 1999 Chi-Chi earthquake. At least that's their hypothesis. I think it makes some sense, but of course it's premature to say for sure whether that's what happened. And there's a coming manuscript, because this is not yet published, I don't want to say much about this, but there is a group led by Hirono and involving several other well-known Japanese and American scientists, which examines the the great Japan earthquake of, where is it listed here? Well, I can't find it, but its date must be on there somewhere. The massive earthquake, the Tohoku earthquake of 2011 in Japan, and asks, could another part of Japan that's seismically active, of the Japan Trench, where the seafloor is likewise dipping underneath the Japanese islands, could that Nankai Trow region to the south be susceptible to big earthquakes? And the way they go about making the argument is they use borings into the seafloor to try to get frictional and poromechanical properties of sediments and ask, could the stuff in the south be susceptible to a thermal pressurization weakening, and hence would it have the potential to let a little earthquake, once started, run away and become large? And at least that's their scenario. It's all a hypothesis at this point, but it's their scenario, and using concepts like I've been going over today as a background for assessing seismic risk. Okay, and let's go back here. I think I have some conclusions. Yes, so what we've looked at are weakening and shear localization processes. They include thermal pressurization of native ground fluid, water, and the volatiles that are decomposition products. We also looked at flash heating of asperity contacts as a weakening mechanism. I did not discuss bulk melting. It's what you get if these other processes can't weaken the fault enough first. It's clear the static strength of the fault is lost here. The static strength of the fault is an unreliable predictor of the pre-earthquake stress on major well-slipped smooth faults. That is to say, the faults are strong, but they are brittle, and if you can do something to nucleate a rupture, it can run over a fault. Roughness may keep less mature faults from the full benefit of dynamic weakening. To slip, the sidewalls have to be deformed if you have a very rough, not very planar fault. And with the Chi-Chi earthquake in mind in particular, the fact that a segment is normally creeping doesn't preclude it from hosting a large coseismic slip. So there are things to think about for the future. Sorry to go so much over time, and thank you very much.
Thanks, Jim. Very informative talk. My question is, over the years, in developing these models, adequate representation has been given to the spatial length scales. And your talk was also in terms of length scales, length of the fault, and the width of the slip zone. But earthquakes happen in medium which is highly heterogeneous. Clays, rocks, each of them have their own intrinsic timescales in which they release energy or they respond to reflected waves. So my question is that the effect of timescales, should they be made a part of the equation for developing models for earthquakes? And secondly, if they should, can they potentially help us in identifying the aftershocks?
Yes, on aftershocks, I think. But I believe it might be another point of view, rather than saying you have all of these complex mixes of lithology, to say the fault zone has kind of created its own lithology. If you have a mature fault that has indeed sustained hundreds or thousands of earthquakes and is well described by a thin principal slip zone, so it may be less relevant that you have a mix of starting materials. Now, what does matter at depth is of course, the way these materials respond to increases in temperatures. Temperature goes up in depth, which might make it impossible in some materials, but possible in others to nucleate an earthquake at certain depths. But if we're just studying the earthquake rupture itself, once nucleated, I think it may not be terribly relevant, all the geometric or material complexity. Certainly if you ask where seismic waves go and how fast, that's very, very important, no two ways about it. And if you try to assess earthquake damage, of course, then the effects of these sediments on or structures on reflecting waves and the like, that's extremely important. But I think for trying to understand the basic physics of strength, maybe it's not too bad an approximation to put it aside is something to get to later.
Okay, so Jim, I have a question about the application of these models to a larger, say, pressure scale. So these are presumably like shallow earthquakes. So if you're going to apply this to like slightly deeper earthquakes, say like beneath the crust, so how deep can we go and what will fail, what will hold still?
Yeah, fair enough. The concepts I've gone through, certainly I'm most comfortable with for crustal earthquakes, and let's say if earthquakes in subduction zones for rather shallow ones. There are lots of other things, or at least some other things that are likely relevant in subduction zones. For example, we often have a situation where if you look at candidate geotherm models for subducting slabs, you find that in ranges which are not terribly deep, let us say of order 25 to 40 kilometers deep or so, the slab itself is undergoing dehydration reactions that are releasing water. So that's another factor in earthquakes in that particular depth range. We think, the we being my student Yijing Liu and ourselves, who've written a couple papers on this, we think the fact that there is dehydration in many of subduction zones is critical to allowing the aseismic deformation transients, which have been much discussed in the recent literature. These are phenomena where, let's say in the Cascades area on our Pacific Northwest coast, the seafloor is slowly sinking under the continent, and GPS instruments, so think of here the seafloor, here the continent, and a GPS instrument here gets pushed towards inner North America continuously, but then over a period of a few weeks to a month, suddenly the instrument moves back a little bit, and then that continues. So these are the so-called aseismic deformation transients, and at least the way Yijing Liu and I have been successful in getting them to emerge from models is to indeed appeal to dehydration reactions that are actively supplying water to the interface. There are a lot of ideas about those aseismic transients, and not everyone agrees on which are the good ideas, but that's one that's out there.
Thank you. Given the relatively brief time that a rupture takes to pass a particular material point, say in your rupture event on an earthquake, is Fickian flow appropriate for the porous model?
I cannot see why it would not be appropriate, but if you ask me what are the experimental bases for saying that, I couldn't point to anything. But if you're not right in that high shear zone, what do you see? You just see that, hey, it's gotten hot fast, the fluid around me wants to expand, and we can estimate what seepage velocities are. They're not so high that you would ever think of, let us say, turbulent flow in the pore space, because the pore space is just too tiny as far as channels go. So I don't feel uncomfortable about it, but maybe I should. So if you have an idea of why I should, I'd like to hear it.
Talk more later, yeah.
Right, so for the sake of time, we will wrap up now, and we have a small gift, a humble one to Professor Rice. And so we have a crystal we can stand over there.
Okay.
From the structures group, just as an appreciation for you visiting us, and are very happy that you made this visit, and thank you very much.
Oh, thank you.